Okay. Hello everyone, welcome to the second week of our Superconducting program. Today we are going to start with Professor Gerhard Kirchmir. Let me briefly introduce him. He is from for Quantum Optics and Quantum Information of the Austrian Academy of Science and is a leading researcher in superconducting circuits and their application in quantum optics, quantum information science, and quantum simulation. His work focuses on using superconducting circuits and junctions to create circuit quantum electrodynamic systems, enabling the study of light-matter interactions at quantum level. Professor Kirchmeyer's research also explores the development of hybrid quantum devices by integrating superconducting qubits with atomic, molecular, and optical systems, with potential application in high-precision sensing and metrology. It is my great honor to invite him for his talk on hot Schrödinger cat states. Welcome, Professor Gerhard.
Well, yeah, thank you very much for the introduction and for the invitation to tell you a little bit about one of the experiments we have recently performed, which essentially uses a circuit QED system to look at some very fundamental effects in quantum physics. But before I start, let me sort of just briefly tell you a little bit about what my group in Innsbruck is working on. So essentially, we have four topics, roughly speaking. On one hand, we are sort of just started very recently working on traveling wave parametric amplifiers, so essentially quantum limited microwave amplifiers to improve the readout of superconducting circuits. We are working on hybrid systems where we are actually coupling superconducting circuits magnetically to a mechanical system. So essentially what you can see here is a little AFM tip with a magnet on top, which couples via a squid to a microwave resonator. Then we are working on what's called waveguide QED. So essentially we use superconducting circuits and embed them in a waveguide. Could be a rectangular microwave waveguide or could be a coplanar waveguide. And the idea here is to look at the light matter interaction of sort of these qubits directly with the modes or the photons in the waveguide, and also sort of the interactions of the qubits in, between sort of multiple qubits. And the idea here is really that you have an open system, so no cavity or nothing, sort of to look at interesting effects like dark state and bright state physics. I won't have the time to talk about any of that, but instead sort of work on tell you more about our work on essentially high coherence microwave resonators and how we control their quantum state with superconducting qubits. And essentially, it's a little bit what you can already see here. We can sort of create Schrödinger cat states in these type of systems. So, but sort of essentially, stepping back a little bit and sort of talk a little bit more fundamentally about, okay, if I think about a system, a quantum system I can control very well, what do I need to observe quantum features? And if one would make sort of a bucket list and go through the requirements, one would typically say, okay, I need purity, so meaning I need to start in a well-defined state. Ideally, it's the ground state. Ideally, it's very pure to actually observe quantum features. Then, of course, I need coherent dynamics. I need to be able to apply a unitary transformation. You can call it gate operations, whatever we prefer, to essentially modify the wave function I started out with and sort of get to sort of the state I want to achieve or sort of do the calculation I want. And then last but not least, of course, I need a measurement to essentially perform the measurements, reconstruct the state, look at sort of the outcome of, for example, a simulation. And essentially, all three of these, so meaning directly there in the center, is where typically most experiments in quantum physics, quantum optics, quantum information sort of want to be located in. That's where I sort of have sort of the best results in some sense. But if you actually look back at sort of Schrödinger's original thought experiment, where he sort of really looked at sort of the fundamental of creating a quantum superposition or entanglement, depending on how you view it. There, it's really sort of he, framed this whole thought experiment in a sense, oh, let me put sort of a cat inside a box and sort of have this photon decay, which then sort of leads to the cat sort of being dead alive and alive at the same time. But in this original Schrödinger's experiment, if you think about the cat as sort of being something that is, a macroscopic object, which is definitely at finite temperature, then this thing is out of equilibrium and is absolutely not the pure state. So meaning the question is, can one realize an experiment where I really put something that starts with essentially zero purity in a quantum superposition? So meaning in sort of this Venn diagram over here, can I get quantum states if I only have coherent dynamics and measurements available? So can I, sort of from a very fundamental question, generate a coherent superposition of a state which originally starts out at zero purity? So meaning a maximally mixed state. And what I'll show you over the course of this talk is that this is actually possible and that we can create quantum superpositions which show real quantum features, even though I'm starting with a highly mixed state of essentially arbitrary temperature. Okay, so after this quick introduction, so here's a sort of a short outline of the talk. I'll first very briefly introduce to you the platform, sort of you're using superconducting circuits and a high coherence microwave resonator. Give you a quick reminder, sort of a quantum optics 101, sort of look at some definitions of phase space, Wigner functions, and so on. And then actually talk about how we generate these, what we call hot Schrödinger cat states, how we measure them and characterize them. And then actually, yeah, I think I won't have the time to talk about our fluxonium experiments, which would have been interesting as well, because that's a separate route, how we could control these high coherence microwave resonators. But let's focus on the hot Schrödinger cat states first. Okay. So what's our experimental platform? We have these very nice, very high coherence microwave resonators. So here you can sort of see one of them cut open, that you can see the inside. That's, in this case, a solid block of aluminum where we milled in sort of a little sort of hole, which has sort of this little post here down at the bottom. This post, you can sort of see the electric field distribution here on the right, has an electric field maximum at the tip and a sort of a node right there at the back. So this is essentially a lambda quarter cavity, pretty much a coaxial cable, which is lambda quarter long, milled out of a solid block of aluminum. We are not only using aluminum, we are also using niobium cavities because it turns out we can produce them with slightly higher quality factors. But what is nice about these cavities is that they are extremely high Q, where extremely means what we've measured in these cavities is quality factors somewhere around 500 million at sort of single photon drive powers. So here you can see the measured Q internal of such a cavity as we sort of increase the drive power. And you see here, this goes to something like 0.5 times 10 to the 9. So meaning these are very, very coherent microwave cavities, sort of very coherent systems to essentially store quantum information in. Now, we have looked a little bit more at these cavities in sort of this paper down here. And we have not only done sort of VNA measurements, so essentially frequency, we looked at the frequency response at the system, essentially saw the resonance curve, and we can extract the resonance frequency and the line width and calculate the quality factor. But we've also done time domain measurements, meaning we apply a microwave pulse, sort of you pulse the cavity, and then in blue you can sort of see a measurement how the cavity actually rings up. Sort of it has a very peculiar shape, but that depends sort of on the way we couple to it. And then we switch off the microwave tone and we sort of see how the cavity sort of rings down and slowly comes back to the ground state. And from this, you can already see that sort of the coherence time of such a cavity is sort of many milliseconds, so meaning actually a very good quantum information storage for microwave photons. But what we actually observed there as well, and that's sort of just a little side remark, is that if you look at this ring down, it turns out it's not just a simple exponential, but actually sort of as you sort of ring down, the sort of decay actually starts to speed up. And this is sort of expected because, as you can see here from these power dependent measurements, sort of the black dots, one would expect, yeah, this should sort of get worse and worse because sort of actually the quality factor goes up for higher powers because I'm saturating two-level defects. But the surprising thing we found is actually that sort of in these cavities, the ring down does not follow exactly the black dots as one would expect, but actually it turns out that sort of the quality factor actually stays higher for even lower photon numbers. And this is actually an effect of, again, the two-level systems coupling to the field I've actually created in the cavity. Pretty much they act as a storage for energy, so they can repopulate the cavity and sort of keep the field in the cavity alive for longer. So it actually only looks like as if the quality factor is higher, where in reality it's sort of just the TLS is sort of feeding back energy into the system. So I think this is sort of just a little bit of a side remark of saying like, okay, if you measure sort of your coherence time of any system, and people have seen similar effects actually for qubits, if you start pumping it and if you start populating your TLSs, interesting things can happen, which, at first glance look like as if your coherence time goes up, but in reality, it actually is just an interaction between the TLSs. Okay, long story short, these cavities are very, very nice quantum memories. So in the end, we want to use it as such, and to control the quantum state in it, we need to couple a qubit to it. So how we do that is actually sort of using a platform which was developed at Yale University. So you have this coaxial resonator I've shown you already. And what we do is we drill an additional hole in from the side where we have a little sapphire piece where we put the qubit on top. So here, this is a simple transmon qubit, a single junction and a little antenna. A part of the antenna sticks into the cavity and couples the electromagnetic field of the cavity to the qubit. And additionally, here in the back, we have a little meandering readout resonator that couples to the qubit, and we can sort of read out on the backside using that pair. So this resonator lets us determine the qubit state, and then sort of via the interaction with the qubit, we can actually change the cavity state and also sort of perform tomography of the cavity. Now, essentially, if you write down the interaction of sort of this high coherence cavity with the qubit, you'll find this Hamiltonian over here in the dispersive limit, meaning that the qubit and the cavity actually have a different resonance frequency, but they sort of have an interaction, and we get this so-called dispersive interaction. So I have the cavity frequency, the qubit frequency. So here sort of I've neglected actually the anharmonicity of the qubit, but the important part is really sort of this interaction term where sort of it has sort of two sides. On one hand, and here you can sort of see measurements, it means that the cavity frequency actually depends on the state of the qubit. So here you can sort of in blue see the cavity frequency for the qubit in the ground state, and then it actually shifts over by something like 2 megahertz in this particular case. And then if the qubit is in the excited state, the cavity shifted to sort of this red line. You can always see sort of a little bit of a dip where, the qubit was not perfectly flipped, or whereas there was some residual sort of temperature in the qubit. So that's why you sort of see a little hump if the qubit was mostly in the excited state, and a little hump if the qubit was mostly in the ground state. Then the flip side of this is, as you can sort of see from this Hamiltonian up here, that the cavity frequency not only depends on the qubit state, but the qubit frequency depends on the number of photons in the cavity. So meaning here, you can actually see sort of discrete peaks in the qubit spectroscopy, where each of those peaks corresponds to a certain photon number. And we know that for no photons in the cavity, this first one is actually the regular qubit transition. And then for every photon I put into the cavity, sort of the line shifts over again by this parameter chi. And in this case, we had sort of a simple coherent state in the cavity, meaning we just drive it with a microwave tone, and then we get a coherent state, meaning sort of a photon number distribution. And essentially, this type of interaction, meaning this dependence of the cavity frequency on the qubit state and sort of the dependence of the qubit frequency on the photon number in the cavity, are the tools that actually allow us to pretty much arbitrarily control the state, the quantum state inside the cavity. There may be some additional parameters. So qubit coherence time, we're sort of right around a few tens of microseconds, so not the greatest qubit, but sort of decent enough for what we have in mind. The cavity lifetime also suffered quite a bit from sort of pushing that cavity chip in. Sort of more recent experiments, we have sort of managed to increase this quite a bit. So how does this look in real life? So I've already shown you sort of the cavity here on the right. So as I said, we sort of drill an additional hole where we can slide in a little sapphire chip. You can see here, if you look very closely, you can sort of see the qubit right there and maybe the meandering line here in the back. This is all sort of inside a clamp, which we sort of bring in through a tunnel from the side. So here you can sort of see the assembled parts, such that this antenna pokes into the cavity and actually couples the qubit and the cavity. Okay, so that's the platform and sort of the fundamental interactions we have available. Now, before we actually talk about how to create a CAT state in this resonator, let me sort of give you a quick reminder on some sort of, quantum optics fundamentals. First, let me talk about driving a quantum harmonic oscillator, because essentially the microwave cavity is just a harmonic oscillator, meaning that if I drive it, so I apply a microwave tone, what I do from an operator perspective, I apply a so-called displacement operation to my cavity state. So meaning what I do is I essentially create a coherent state in the cavity if I apply a microwave drive tone. Such a coherent state alpha, so actually alpha is a complex number with sort of an absolute value and a phase, is a superposition of Fock states in the cavity with sort of, again, sort of some amplitude and a phase. So these states are, very classical, and the easiest way to see this is actually by looking at them in phase space, because essentially what you have is an almost classical state. It has an amplitude, it has a phase, and sort of in this phase space picture where I sort of plot the expectation value of position and momentum, or the two quadratures, sort of I and Q, or the real and imaginary part of this alpha, sort of everything's sort of the same here. This coherent state I create is essentially just, I start in the vacuum, which is sort of actually sort of for a classical phase space would just be a point in the origin. And then if I apply a displacement, I go out to some finite value alpha. And then sort of what would happen for such a coherent state, it would sort of, like you would expect for a classical stage, sort of just rotate in phase space with the frequency of the microwave cavity. So meaning if I'm in some rotating frame, where the frame reference is sort of my microwave drive, I would have sort of a picture that stands still. Now, of course, this, because it's a quantum state, this is not just a point in phase space, but actually this is a distribution. And as we'll see in a little bit, a displaced ground state is actually sort of a Gaussian in this phase space picture. Now, if we have sort of this phase space sort of describing the state of the cavity, we have to have some means of actually measuring the state we have there. And one of the ways to do it, and I think the easiest one to understand, is actually measure the so-called Husimi Q function. So we want to measure pretty much the phase space distribution of the state we create. And sort of this Q function is defined, as you can see here on the left. So meaning I create some state rho in the cavity, and then I ask the question, okay, what's its overlap with a coherent state at location alpha? And that's sort of the value I plot in phase space. Maybe a more intuitive picture is actually describing it in the way we measure it, meaning I take my state rho, I apply a displacement. So again, I move it in phase space, and then I ask the question, okay, what's its overlap with sort of the ground state, meaning having no photons in the cavity? So maybe more pictorially here on the right. So I have some, state I created in the cavity, whatever it looks like exactly. So what I do now is I sort of start with that state, but I now apply sort of the displacements I sort of just talked about. So for example, I bring it back close to the ground state, and then I just, try and measure the probability of being in the ground state. And I do this, so this gives me 1 pixel. At sort of location where I did my displacement from. And then I can sort of do other displacements and sort of pixel by pixel build up this whole phase-space picture and get sort of a pretty good idea of the distribution in phase space, sort of where I actually have a state by just measuring the overlap with the ground state. Okay, so I have to do this sort of pixel by pixel. The question that's left is, okay, how do I measure what's my overlap with the ground state? So what's the probability of, after doing this displacement, finding no cavities in, no photons in the cavity? Well, actually, I already talked about the ingredient, and that's sort of, we just use our photon number splitting on the qubit. Meaning, if you look at the photon number splitting, so here's a slightly different measurement to the one I showed before, I get sort of these discrete peaks, and the separation between the peaks is actually chi. So meaning this guy sort of here, this first line actually corresponds to having no photons in the cavity. The next one over is 1 photon, 2 photons, and so forth. Meaning these peaks are spectrally well resolved. So that actually means I can deliberately flip the qubit if and only if there's no photon in the cavity. So meaning I can just apply a pi pulse to the qubit, and I just have to make sure that the pi pulse is sort of long enough such that its Fourier transform is sort of narrow enough that I make sure I only flip sort of the n=0 state and not any of the others. But such a simple actually pulse allows me then to flip the qubit conditioned on the number of photons in the cavity. So I could do this for any Fock state. What we do for measuring this so-called CMQ function is flip it for n=0. Okay, so meaning I have now this conditional operation on sort of the conditional operation on the qubit conditioned on the cavity state. So if we then do this, so meaning we first create a state, in this case, it's a simple displacement I apply, then we do all of these analysis displacements, so sort of measuring every pixel in phase space, and for every such displacement, we then have to sort of do this selective pi pulse and then, measure the state of the qubit and repeat this many, many times to get the statistics. And what we find for such a, displaced coherent state is actually, well, it's just a two-dimensional Gaussian in phase space. So here you can sort of see I've taken the ground state, which would be sort of centered here at 0, 0, and I've displaced it out to a value of sort of 2 alpha. Okay, so meaning that allows me to sort of measure and visualize what goes on in the cavity. And actually, this is already all the ingredients we need to actually create a Schrödinger cat state. So how do we do that? Well, so we start out by having the cavity in the ground state and the qubit in the ground state. So what I then plot over here is sort of a combined phase space cavity picture where sort of the qubit state is additionally encoded in the color. So we start out with both of them in the ground state. Then the first thing we do is apply sort of a pi/2 pulse, meaning I go from blue to pink, but nothing happens inside the cavity. Then we apply this displacement, which sort of kicks the state out to some finite amplitude here. And now what happens is actually that the cavity starts to separate into 2 states. And that comes from the fact that the frequency of the cavity now depends whether my qubit is in a ground state and the excited state. So if my qubit is in a superposition, my cavity at the same time has 2 frequencies, meaning the half where the qubit is in a ground state will stay put, whereas the other one will start to rotate exactly at the difference frequency, and this difference frequency is calm. So here, sort of, I've chosen my rotating frame with respect to the cavity if the qubit is in a ground state. So now, sort of, the state starts to rotate over onto the other side of phase space, such that I have a state alpha with the qubit in a ground state and a state minus alpha with the qubit in an excited state. And now we can actually create, so at that point, in some sense, we've already created a cat state. Yeah, so this is sort of similar to, a photon decayed in Schrödinger's thought experiment with a certain probability. And sort of my cat is then sort of dead or alive with a certain probability, where here the probability is just exactly 50. So we can now disentangle the qubit and the cavity state by sort of applying another displacement, which shifts everything to the right, such that the excited state of the qubit is now at sort of no photons in the cavity. I can now run this conditional operation, sort of flip my qubit state if and only if there's no photon in the cavity. This brings everything back to the ground state, and now I'll shift over, and now I get this what's called Schrödinger cat state, meaning a superposition of alpha and minus alpha in the cavity, or in other words, I have sort of two simultaneously two electromagnetic waves in my cavity, which have the same amplitude but opposing phases. And the funny part is they don't cancel each other, but they live in the cavity at the same time. Sort of, this is really sort of a quantum superposition. And now, what's kind of hard to actually experimentally verify using the Husimi Q function in an experiment is whether this is just a classical mixture. So sometimes I have one state, sometimes I have the other, or whether it's actually a coherent superposition. For this, one would actually measure a different observable instead of this sort of Husimi Q function. One would measure the so-called Wigner function. And the difference here is that instead of measuring sort of what's the probability of being in the ground state, I look at the so-called parity of the state, which translates to, is the photon number of my cavity in the cavity even or odd? If it's even, then I assign a +1 value to it. If it's odd, I assign a minus value to it. And what then happens for this cat state picture is actually that I still have my coherent state here on the right, my coherent state here on the left, but now I additionally get this interference fringes. You see sort of here my parity value goes from a +1 to -1, or from positive to negative, and so on and so forth. So I get this essentially interference pattern between those two halves, and that's a signature for a real quantum state. So if I see these fringes, I can be very confident that I actually have a quantum superposition in the cavity. Now, these states are nowadays used actually for so-called bosonic codes, meaning actually such a cat state can be used for quantum error correction, can be used for sort of creating very biased qubits, where I sort of use some dissipative engineering such that sort of this superposition is kept alive. So they don't just look pretty, but they're actually useful. Okay, so now about here, for this cat state, we've actually started out with the cavity in the ground state. So we've cooled it down in our cryostat at sort of these temperatures. The cavity is very, very cold, essentially has no photons in it. So meaning I start out with a very, very pure state. The question is now, what happens if we sort of artificially warm up the temperature of the qubit? Meaning, what happens if we add thermal noise to the system? So in this case, we are creating a very, very classical state to start with, something which essentially has no purity. And the question is, can we still create this quantum superposition? So we are warming up our system actually by essentially just injecting noise, injecting thermal noise into our setup. We do this by essentially just taking a 50 ohm resistor at room temperature. So we just have Johnson-Nyquist noise. We then sort of put the coupled amplifiers afterwards to amplify this Johnson-Nyquist up this Johnson-Nyquist noise up, to sort of a large enough power. We sort of put it through a filter to make sure that we only heat up the cavity. Sort of we want to keep the qubit and the readout resonator cold to still be able to do coherent control. And then we have sort of an additional digital attenuator to be able to vary sort of the power we send to the cavity and a switch to sort of switch it on and off. So if you look at sort of the noise that comes out of the setup, it's sort of very much concentrated right at the cavity frequency, which in this case was around 4.5 gigahertz, but it falls off to almost zero where our qubit frequency was, which was like 5.5 gigahertz. So with that setup, we can sort of really control in some sense the environment or the temperature of the environment of the bosonic mode. Meaning we can actually now look at what happens if we inject noise, and we can again just measure the photon number distribution in the cavity. So what you can, for example, see here, if we apply this noise. So meaning again, this first peak here on the right is no photons in the cavity, and then it's 1, 2, 3, and so on, photons, because we've sort of injected this noise. So what you see here is essentially this sort of thermal distribution we would expect, sort of following essentially this equation here, meaning we can now, by fitting this data, extract sort of an effective temperature or an effective mean thermal population of the cavity as we sort of inject more and more noise. And we see essentially this follows a more or less sort of linear trend where for sort of very high noise per hours, it sort of gets trickier and trickier to measure because we have to measure out to higher and higher photon numbers, but each peak sort of becomes smaller and smaller. But in the end, we have a sort of reliable means of controlling the temperature of the cavity, and we can warm it up to something like effectively 1.5 Kelvin. So really sort of it's the mode temperature and not the real temperature of the device. The real device temperature, sort of the bulk aluminum, still stays at a few 10 millikelvin. It's just that the mode was effectively heated up to this. Okay, so if we now sort of think about these thermal states and sort of look at them sort of in phase space, so here, this is again sort of just a simple Gaussian coherent state, meaning I started out with the cavity in the ground state, so no photons. In this case, sort of it has a sort of a maximum purity. If I now look at sort of a much lower purity, then sort of you see in this phase space picture, the Gaussian actually becomes much wider and it actually blurs because it sort of just broadens out. So essentially what happens if I inject noise is sort of it becomes wider in phase space. Sort of a typical way to view these states is normally actually sort of a phase, sort of a Fock basis where I sort of look at sort of this sort of state as sort of a mixture of all the different Fock states, which sort of follow this probability distribution I've shown you before. But this is sort of a very classical mixture. There's no quantumness sort of in this state, really. Turns out to understand what goes on in sort of the creation of these hot cat states, it's actually easier to not think about this thermal distribution in this Fock basis, but think about sort of rather in a coherent state basis, meaning instead of building this up photon by photon, I say like, okay, what I can do instead is I say, okay, I have a statistical mixture of slightly different displaced vacuum states. So we try to sort of signify this with sort of this compass-like state. So each of those colored circles is sort of one part of an ensemble of sort of coherent states, and a sum over all of them with the right distribution would sort of give me this thermal state up here. And then additionally encoded here is the sort of state of the qubit as sort of this little diamond in the center, and the colors the state. Okay, so with that, we can actually now have a look at what happens if we start out not in the ground state, but at a sort of a thermal state. The sequence we actually used to create the cat state, I've pretty much already run through. The only additions are I first inject noise into the cavity to heat it up to a certain mean thermal photon number to a certain temperature. Then I run this sequence I already described to you. So we have this pi over 2 pulse, the displacement, waiting time, again a displacement, and then the conditional operations to sort of get the state. So meaning in this case, what happens is this V1 here is literally just this simple rotation phase space I've already shown. We have not only run this protocol, but we've also run what's called a conditional echo displacement routine, where sort of we stop the rotation in some sense halfway. We do a little bit of a displacement, and then we essentially apply a spin echo pulse. So this is this Y here, which essentially just flips the qubit state. So meaning, you see, this was ground state first, and then we sort of flip it over such that this state now stays put and the other one rotates. So here we sort of split up the rotation, only half of the, at first one half of the state in the cavity rotates, and then the other, instead of the rotation is done all by one state. So these are the sort of the two protocols. This one here with the spin echo, we have only done because we wanted to make sure that we could possibly take out some qubit dephasing in the state creation. Okay, so now what happens if we start with the thermal photons in the cavity? Well, actually, we can create cat states. So here we started with a mean photon number in the cavity of like 3.5, so really thermal photons, meaning we started out with a purity of 0.13. So really, almost, there's, not much. This is really a sort of a statistical mixture we start out with of different photons. But still, we can see very nice interference fringes. So for example, here in sort of on the left, this is actually using this standard sequence. You can see that the sort of actually in phase space, the distribution actually broadens. So this would be sort of for a cold cat, the circle, and you see it's much wider now because we have these additional photons in there. We have the same here on the left, but we still see very, very nice interference fringes. So this goes very clearly positive and negative. And here, just as a comparison, you see some simulation we have performed. So this confirms that we should still see these fringes. The surprising fact for us was actually that if we run the other sequence, the state we get out actually changes. You see, it's still sort of very wide here, but now these interference fringes of being sort of, instead of being concentrated right here in the center only, they spread out over a much wider region. And actually, in some sense, they sort of connect to the Gaussians. It turns out, actually, this is also confirmed by simulation if you sort of put in our sequence. But essentially, depending on the sequence we run, we get two very distinct cat states, which is actually not the case if you do this for a cold cat, meaning if I start out in the ground state, the two cats I get out will be essentially identical. But what this already shows is that we can create these superpositions even if we start out with sort of a finite number of thermal photons in the cavity, starting out with a very, very mixed state. Now, the question is, why do we see these two different cat states? Well, it's really sort of coming from the sequence. So if you look at sort of these two protocols, it turns out for the simple QC map and sort of now sort of taking this compass state where I sort of start out like with symmetry or sort of the 4 dots arranged like you can see here. If I take the simple QC map, that guy sort of just rotates over on the other side. So meaning this slightly displaced coherence state to the top, rotates to the bottom, the inside, the yellow stays inside, the outside stays outside, and sort of this sort of blue one rotates to the top. So here what we actually get is sort of a point-like symmetry, meaning I'm really sort of symmetric around the origin in this case. For the one where we sort of add this additional pi pulse, it turns out the symmetry of the state changes, meaning if I started out on the top, this other copy in some sense will have the same state on the top, bottom, and bottom. So meaning if you think about the interference fringes, I will always have interference between sort of the same colored dots, meaning here on the left, I just get different cat states, which are just slightly rotated in one direction, rotated in the other direction, are a little larger, are a little smaller, but all of them sort of add up constructively in the center, so we will see a nice interference fringe. Whereas here on the right side, what I get is sort of, again, cat states, but all of them are slightly displaced, meaning my interference fringes will become wider and wider, but they will also wash out and become lower. Sort of, if you sort of look at this sort of two states and what we effectively realize, if you sort of prefer an operator language, actually one of them, sort of the second operation, let me start there, create what's called a state-dependent displacement operation, meaning I at the same time displace my cavity to the left and the right. And the other, this simple sort of sequence, which just has the rotation, no pi pulse, effectively implements a displacement and then on top sort of a parity operation sort of applied to the cavity state. So this gives us sort of here some theory plots, these sort of two distinct Wigner functions, where in one case, the hotter I go, sort of these fringes become wider and wider, but the contrast actually shrinks. And in the other case, actually the contrast of the fringes always stays full, so they go from sort of to maximum or minimum parity. But as I go hotter, this narrower and narrower, this sort of region becomes where I see interference fringes. The nice thing about these operations is you can actually analytically calculate what interference pattern you get. So here, this is sort of the Wigner function, sort of analytical expression for the state here on the top left. So you have your two states where you see the hotter I make them, sort of this is essentially just reflected here in the purity, this parameter P, sort of the wider these Gaussians go in phase space. But actually the interference pattern, which is sort of this term here, actually goes as 1 over P in the exponential in the Gaussian. So meaning that one becomes narrower and narrower the hotter I make it, but it still remains full contrast. You see, this is, there's no purity prefactor, so the Gaussians become lower, but the interference fringes stay the same height. For the other one, it's actually, this purity is a prefactor to the whole expression. And in this case, sort of this Gaussian, which has the interference pattern, actually becomes wider and wider and wider, meaning, sort of they go further, but the overall contrast goes down. And this is sort of essentially what we have seen for the two cats. So in one case, we see the pattern, sort of the hotter we make it, the narrower it gets. And in the other case, it sort of gets wider. Here, sort of the contrast stays nicer. You see it's sort of a little more dark blue here than over there. So in some sense, the parity here is better preserved than in the other one. Now we have not only done this for sort of this one temperature in the cavity, but we've done this for varying mean thermal photons, so up to something like 7.5, 7.6 photons, thermal photons in the cavity. And you can see for the sort of simple sequence, we always see sort of a nice, well-separated peak here in the center with sort of nice interference fringes. We can still see interference fringes for the other one, but everything sort of blurs together a little more. The contrast is also lower. But still, in both cases, we can actually realize this quantum superposition, even though we have started from very, very impure states. And so this is really sort of a quantum superposition of a thermal state on the right and the thermal state on the left. And maybe the funny part here is the purity sort of for these higher states is something like 0.05, and we still see quantum features. If you compare this to, for example, a completely dephased cat, so meaning I've really created a statistical mixture of a left and a right Gaussian, so meaning a very classical state, this actually still has purity 1/2, just because my states are still coherent states on the left and the coherent state on the right. So meaning we have something here which has lower purity, it didn't change during our sequence, but it still sort of shows very pronounced quantum features. So meaning it's really sort of a quantum superposition of a very classical state on the right and a very classical state. Okay, with that, I'm almost at the end. So here we've just, because this question comes up again and again, what about the lifetime? Turns out the lifetimes of these thermal cat states does not depend on sort of the thermal population. All of them sort of decay with pretty much the same decay time. And this decay time is essentially just given by sort of how large of a cat state we create. And we measure something like, about 3 microseconds for the cats we create. What we calculate is slightly longer, but this is just because we need some time to measure the state where it can additionally decay. So if you sort of add up those two numbers, you get it pretty much exactly to the calculated state. These cats are good quantum superpositions, but as you might have noticed, sort of the theory and the experiment don't always agree perfectly. So here you can again sort of see the experiment on the top and here, and the perfect theory, sort of assuming I would have an ideal system. So what we've done is sort of we have step by step sort of added non-idealities, like our cavity, because it couples to the qubit, turns out is not a perfect harmonic oscillator anymore. It gets a nonlinearity or a so-called Kerr effect, which leads to the bending of the fringes. Of course, we have some decoherence in the system, which leads to a decay of the fringes. And the actually largest part is it turns out the qubit pulses are a bit more complicated, because in this case, I can't be as perfectly selective anymore. But what I have in the cavity, instead of just a perfect ground state peak, is I now have sort of a thermal distribution if I displaced my cavity back. So meaning now my selective pulse can't be selective with respect to having no photons in the cavity, but we have to make sure that we flip sort of all of these photons or the qubit state for all of these photons, but ideally not affect sort of any of sort of the high photon numbers which correspond to sort of the state being out there. So this is sort of a bit trickier and harder to do, and that sort of also leads to some of the discrepancies, sort of bending of the fringes you've seen, or sort of these little sort of additional fringes down here at the bottom, which are not there for the ideal theory, but if we sort of put in all the effects, we can actually nicely reproduce it as well. So yeah, with that, I'm actually at the end. So I hope I could show you that even with zero purity states or something very classical, you can create quantum superpositions. So meaning actually purity is not a requirement to sort of see quantum features. This has sort of interesting consequences for some of the optomechanics experiments, where sort of they try to essentially cool mechanical systems close to the ground state to then be able to generate non-classical states for sensing applications, or essentially testing quantum physics on macroscopic scales. It turns out what we show here is that if you have the right interactions available, you don't even need to do ground state cooling, but you can get away with much higher temperatures. The question is, what is it good for? Are there any applications? Well, it just shows that you have to think a little bit about if you have some residual photons, it sort of can lead to different states you create. Maybe one can use them for quantum metrology, but that's sort of, still open questions. One thing I sort of wanna add as well is that there's actually no fundamental limit, meaning I can make this cat as hot as I want. As long as I can displace them far enough in phase space, I can always create this quantum superposition. Now, for a real experiment, I of course run into limits in terms of coherence or in terms of higher order effects in my system. But just from a pure theoretical perspective, there's no limitation on how hot the system can be. I should still be able to observe a quantum superposition no matter what the temperature. And then, as I mentioned, these bosonic codes use these cat states. And here, it's sort of important to sort of take into account when I create a cat state to stabilize it, that I sort of pick the right sequence to sort of maximize the parity. As you've seen, sort of parities are quite different in two cases. And with that, I'm actually at the end. Let me just sort of show a picture of the group, right in front of the mountains here in Innsbruck. And sort of the two PhD students on the project are Ian Yang, so which did most of the measurements, Vasilisa Usova, who helped a lot with experiments and simulations, and then our theory collaborators, Oriol Romero Isard and Thomas Agrenius, sort of a PhD student of Oriol, for sort of in the combination we have sort of experiment and theory to describe everything. And with that, I'm actually at the end, and thank you for your attention.
Thanks for this great lecture, Professor Gert. If you wish, we can just continue with questions. There are some exciting questions waiting for you.
Sure.
The first one is, how are the properties of the microwave pulse related to the response of the cavity when probing it to obtain its characteristics?
Right. Yeah, that's a very good question, actually. So maybe let me go back a little bit. So essentially, one thing we have to make sure is that, so for example, here, the microwave pulse to displace the cavity has to be relatively short, meaning it has to be, in our case, it's a few nanoseconds pulse. And the reason why we make it very short is to make sure that sort of during the time we apply the pulse, no rotation happens, meaning my two states don't start to separate. This is not a strict requirement necessarily, but it makes life a little bit easier, because then I can think of these displacement as essentially instantaneously, because this chi is typically sort of a megahertz or so, so meaning rotation time is a few hundreds of nanoseconds. So if I make it much faster, the pulse is much shorter than this, displacements are essentially instantaneous. Right.
Okay, thanks a lot. And the second question is, what is the nature of interactions between two-level systems and cavities? Does fully understanding these interactions enable us to coherently control TLSs using cavities?
Okay. So also a very good question. So in the cavity case, it's essentially just a dipole-dipole interaction, meaning the dipole moment of the TLS couples to the electric field in the cavity. In the cavity case, though, the coupling is actually rather weak, because these TLSs sit on the surface of this cavity I've shown, and they interact very, very weakly with the cavity, but there's many of them. So meaning I have sort of a very thin layer here only at the wall or maybe at the post. So there is, many, possibly, a couple, I don't know, 100,000 TLSs, which couple very weakly. So I sort of couple to a whole ensemble of TLS systems. But all of them, in some sense, are coherent, or we have some coherence in them, coming essentially just from being coupled to the same cavity field. So they can sort of inject back energy at the right phase. So I can't really. So it's essentially what these measurements allow me to do, and we've shown this sort of in this presentation. In this paper I've highlighted. That we can sort of look at, okay, how strongly do we couple to these TLSs? What type of couplings do we have? But it doesn't really allow us to control the TLS. Really, it's an additional means of characterizing them. I think for qubits, people have shown, even in the past, like sort of already 20 years ago, that I can couple to TLSs very strongly, and actually I can then use my qubit to control the quantum state of the TLS. I think there are some Martini's experiments from, I guess, almost, maybe 15, 20 years ago, where they've shown that they can coherently swap an interaction into the TLS and back out again. But this is sort of particularly strongly coupled TLSs, which I normally don't want. No, I want to get rid of all the TLSs, and if they're still there, I want to couple very weakly to make sure that my quantum circuit has the highest possible coherence time.
Okay, thanks a lot. And next question is, what is the effect of environmental thermal noise? Does it disrupt the control thermal noise that implied external, or is it still negligible since aluminum is in millikelvin?
Okay, so sorry, can you repeat? It's sort of the thermal noise.
Yeah, I'm asking what is the effect of environmental thermal noise? Because you're implying a control
Ah.
thermal noise that is in high temperature.
Mhm. Oh, you mean the environment? Okay, yeah. So the cavity itself is at a temperature of a few tens of millikelvin. So meaning if we measure what's the residual excitation we have in the cavity, we typically find a percent or two. So something relatively low. Meaning the cavity is almost perfectly in the ground state up to sort of a tiny little bit, which most likely is actually not even coming from the physical temperature of the cavity, but rather is just anyways noise coming in via the controller.
Okay. And the next question is, you mentioned two way of creating hot cat states.
Mhm.
And as you know, in the bosonic cat state, it needs to be applied a stabilize driver, like two photon driver to
Mm.
stabilize the cat qubits. And does it also necessary in hot Schrödinger cats or like a constant head transfer?
Okay, so I mean, if I apply sort of if I use two photon dissipation to stabilize a cat, and two photon dissipation is parity preserving. So meaning I could effectively um, um, also use this on a thermal cat. What would happen though is that as this is a dissipative process, and if you sort of look at the sort of how should I say it, attractors in phase space, effectively my thermal states would cool down and they would become nice Gaussians. The only thing that wouldn't change is sort of the height of the parity fringes I started out with, because this sort of two photon dissipation is parity preserving. Meaning if I started in the wrong cat, so meaning if I started in sort of the one with the sort of wider fringes, um, then so if I start with the one here on the right, which has sort of a lower parity than the one on the left, in some sense for measuring a stabilizer, the right one would be slightly worse, yeah, because I would already start off with a certain probability of measuring the wrong parity. Whereas the one on the left, in some sense, is a better starting point for applying my two photon dissipator. And this is really because this two photon dissipation is parity preserving. The Gaussians, again, would sort of shrink down, but the parity would just stay what it is.
Okay, thanks. And the next question is, if noise is only applied to the cavity, what causes the phasing in qubit that a spin echo is needed in the protocol?
Ah, very good question as well. In this case, we will sort of essentially there's two things to it. No, there is photons in the cavity which will sort of randomly let the qubit frequency fluctuate. Now, depending on the lifetime of the cavity, I can then echo this out, but typically thermal noise in the cavity I can't echo out. But there might be other dephasing mechanisms, and if they're sort of slow enough, we could potentially benefit from sort of a high pulse, sort of a spin echo on the qubit. It turns out, sort of, if you look at the parameters, our echo times of the qubit are, sorry, where do I have them? I think I had them somewhere. Okay, so our echo times, our spin echo times for the qubit are slightly longer than sort of the pure T2 times or T2 stars. So meaning we hope to benefit a little bit from applying this additional spin echo. It turned out it didn't help. It didn't change much. Yeah.
Okay. The next question is, why we see negativity in probability distribution even in an impure state?
Why? Sorry, can you repeat again?
Yes, of course. Why we see negativity in probability distribution even in impure states?
I mean, but that's the whole point. No, it's a very impure state. I totally agree. So meaning we did not change the purity of the state, but the point is the states we create, they are yes, they are a statistical mixture of photons, but there is still coherence between sort of the right side here and the left side there. Yeah, and this is really sort of this picture I was trying to draw here. What I have is uh, for every realization, sort of randomly sort of pick one of those 4 points, or actually, of course, it's a whole distribution over all of phase space. But for every point out of this ensemble, I actually create a perfect cat. So meaning for the green one, I create a cat which is there, diagonally. For the blue one, it's diagonally in the other direction. The yellow one is a little smaller. The purple one is a bit bigger. And then I have to add them up in sort of a statistical mixture. But it turns out there is then, if I ask the question, is there coherence between the left and the right? The answer is yes. And unfortunately, I don't have this here, but you can also calculate what's called the coherence function of the state. And this one shows sort of that if we calculate this for our state, it shows that yes, it's actually a coherent superposition. So meaning I have a state on the right and a state on the left, but purity is zero. I think what my takeaway from this is that purity is actually a very bad measure for saying something is classical or quantum. I can have, as this sort of proves, almost zero purity state. Yeah, sort of the hottest cat we have created had 0.05. So for this 7.5 photons had 0.05 purity, but really still showed quantum features.
Okay, and our last question is, as you mentioned, the lifetime of these states does not depend on the thermal distribution. Where does this resilience come from?
Okay. So it's sort of that's actually, if you look at the theory, that's how the lifetime of a cat is given. And this NB is actually not sort of whether I create a thermal state or not, but rather whether I'm coupled to still a bath at a finite temperature. So meaning, maybe I didn't explain this well enough, this lifetime is always the same, no matter how large the thermostat was created. But what we do for the cat is after we inject the thermostat, we actually disconnect the bath. If we don't do this, actually the lifetime of the cat goes down, but not because we have created this thermostat in the cavity, but because we are still coupled to a hot bath. Yeah, because it sort of gives us additional fluctuations. And then otherwise, sort of if I don't have this bath, so it's disconnected, so this NB is zero, it only depends on the size of the displacement. Yeah, meaning it's sort of essentially just depends on how distinguishable in some sense are sort of the coherent state on the left and on the right. So meaning yeah, sort of how likely is it that I lose a photon? So meaning essentially the larger alpha goes, so alpha squared is the photon number, the mean photon number, meaning my lifetime of the cat just goes down with this mean photon number. The larger I make it, the lower it goes. But the distribution in phase space, how wide it is, actually that has no effect.
Okay, thanks for all your answers and this enlightening presentation, Professor Garrett. I think we can end now.
Yeah, thanks for all the nice questions, and yeah, thanks for giving me the opportunity to present our results. And yeah, I hope you have another couple exciting talks through the rest of the week.
Thanks a lot.
Bye, everyone.
Great. And now we are going to start our first tutorial in the program with Sadman Ahmet Shanto. Sadman Ahmet Shanto is a PhD candidate in physics at the University of Southern California, specializing in the development of superconducting quantum devices and improving qubit coherence and dephasing times. He has published several papers in quantum information science and has experience in experimental and theoretical quantum hardware research. Additionally, Shanto is one of the main developers of SQADDS an open source database of superconducting quantum service designs. It is my great honor to invite him for his tutorial on SQADDS. Welcome. Oh, I think.
Everyone,
Okay.
can you hear me?
Yeah.
All right.
We can hear
Thank you,
you.
Karen. Yes,
Welcome.
thank you for the nice introduction. I'm surprised you know so much about me. um, yes, I'm again Shanto, fourth year PhD student at the Levinson Pulse Lab, and today I'll be doing my first tutorial presentations out of three, which will be seeing a lot of me over the next 3 days, and I'll be talking about squads today. This started off as a side project in our lab, really, which we're very happy to see that the community has really embraced with open arms, and it's growing to be even more popular and important than we initially expected it to be. So I'm very excited to get y'all onboarded on this project. I want to start off with a couple of slides from Eli's talk earlier last week, just so everyone's kind of has context about what this project is all about, and or people who missed the talk maybe get the chance to learn about it a little bit. And we have, again, the shared context. So my screen is being shared, right? Just wanted to make sure.
Yes, it is shared. It's
awesome. Cool.
No problem.
Again, as Eli kind of mentioned in his talk, in a very typical superconducting quantum workflow, we have some system Hamiltonian in mind that we want to study. It is not at all obvious how that Hamiltonian would look on a chip. So we really do start with an educated guess, and we simulate that using FEM simulations solvers such as ANSYS, COMSOL, whatever. And we do quantum analysis on these simulation results to get the Hamiltonian parameters back, and then we kind of see how far away we are from our desired Hamiltonian parameters, and then we change the design, simulate again, and iterate on this process until we see that our simulations are kind of giving us the design layout that we want. And at that point, we usually go to the clean room and fabricate that device and measure it to see that the parameters are nowhere close to what we wanted it. And most likely than not, we then use reality as our simulation and move on with it. Again, not that it needs to be said, but this is a very expensive, both in time and monetary-wise process. The idea with squads is that we provide a database of dense, validated, and accurate simulation results, and also measurement results, and a simulation methodology that people can use to essentially have a single shot workflow from the Hilbert space to the clean room. And so the idea is that, as I'll kind of show you all today, is you input your Hamiltonian parameters to the squads database, and it will give you back a design file that you can then, with pretty high confidence, fabricate and get the parameters that you want to have in your device anyways. So that's the idea with squads. Again, to put a little bit more formally in a cartoon, the problem that we were trying to solve is essentially, again, you have a point in Hamiltonian space and you want to find out where it lands in the design space, which can be horribly large. And it's not an easy to solve problem at all. How we end up trying to approach this problem and solve it is that we solve the inverse problem, where we do have a device that we've made whose design space parameters we know. It is in our fridge and we've done all the measurements. So we also know its corresponding Hamiltonian space parameters. So essentially we know this mapping between the spaces. And then we simulate this device. Now, of course, there is no guarantee that the simulation would land us anywhere close to the vicinity of the Hamiltonian space point that we want it to be. But we know that simulations done correctly with the right methodology and hyperparameters approximates reality. So there is a validated simulation pipeline that connects our design or our device to this Hamiltonian space point. And the idea with squads is that we found these validated simulation pipelines and we've open sourced it so that everyone else can also use it. And how we build this squads database is that once we find this validated pipeline, we make local changes to various design space variables, and we populate the database with these new local changes. And then For the actual database, we use combinatorics to combine various data sets together to have an even denser database. So in a nutshell, Squads is a combination of a database, which we host on Hugging Face, and a Python API, which essentially helps the user to query and access a bunch of information from this database. Again, the API is not really required if people are savvy enough to just look at the database and look for the data over there. But we hope the Squads API makes it much, much easier for the superconducting quantum community to interact with the database. So that's Squads in a nutshell. In today's tutorial, I'm going to talk about what the database structure looks like for Squads, since we're using a not so traditional Hugging Face data set, but it's becoming ever so more important in the computational science landscape. And I would also kind of go over a minimum viable use case for Squads that people can use to query the database and get some designs out. So that's the idea for today's tutorial. And now I'll share my Jupyter notebook, which I'll make available after my talk. Oops. Okay. Is my screen still shared?
Yes, it is visible.
Awesome. Cool. So let's get started. So first thing, I did put a message on the Discord server yesterday about installation guide. Again, I have a link to it over here as well. I've tested it on various Windows, Mac, and Linux distros, and it should be working fine. There's also a Docker image if anyone needs to pull that up to run Squads as well. But one thing I would like to make sure is that everyone's running the 0.3.6 version of Squads. And again, if there's issues with installation, please put messages on the Discord or the GitHub GitHub discussions page that I created, and I will get back to you all. Okay, let's understand a little bit about the database structure on Hugging Face. Now, Hugging Face is not again, traditional SQL-based database, right? It is essentially a structured collection of what they call is configurations. An analogy for configurations to the more traditional database systems is that it's kind of like what the table is. And how, for Squads, the table ID of how we set it up is essentially a string of 3 variables, where the first variable is a component. It is essentially the circuit QD element that you're interested in. For example, it can be a qubit, it can be a cavity with claw, it can be a filter, the stuff that we have available in the data set. And a component name, which essentially specifies the type of component. And the component name must be a string available in Qiskit metal. So for example, if you have the component being qubit, component names can be transmon cross, transmon pad, transmon star, whatever Qiskit metal has support for and is available in the database. The data type variable represents the type of simulation data that has been contributed. So that's just how the configuration is defined in Squads. Let's start accessing the stuff. So for Squads, there's like 3 big classes that are actually for today's talk. We'll talk about 2 big classes that we'll be dealing with. One is the Squads DB class, which is a singleton class needed to make a very fast, non-latent connection to the database. So we would always initialize this DB instantiation or the Squads DB instantiation in Squads. And to check for the various configurations or the various tables in our data set, we can use this get configs method. And as we can see, there's like 4 entries or 4 types of data points of data sets available in the Squads database presently that we can publicly share. One is qubit, we have transmon cross support, and we have a bunch of capacitance matrix results. One is a cavity claw structure, which is of type route meander in Qiskit metal, and we have eigenmode data on it. And one is the coupler, which we have a deprecated version and most present version for it, but it's the same data set really. But it's the cap and interdigital T sort of Qiskit, it's a Q component in Qiskit metal, and we have capacitance matrix simulation results on that as well. Using this view datasets method, we can also kind of see the same information, but let's say if you did not know what these components look like, there are these links available that you can click to see visually what those few components look like. So if you want to get more information about a certain data set, for example, you want to look at what the qubit transmon cap matrix configuration looks like, you can use this get dataset info method, and it will provide to you all the dataset features for the entries available. So for example, there's 4 columns in this dataset: contributor, essentially, and again, contributor is a dictionary with a bunch of information of who contributed this data; a design column, which includes a design options dictionary, which essentially, for people who are experienced with Qiskit Metal, this is the meat of the data set, in the sense that this contains all the information needed that you can then parse and send to and instantiate your Qiskit Metal components with; and a design tool, which kind of tells you which design tool has been used to create, or which design tool has been used to create this design, which design options map onto this. So for now, I think most designs that we have are made in Qiskit Metal, but there is no reason why we can't grow to other design tools if the community as a whole decides on adding more design tools to this field. So we have that. Notes, if people want to leave any notes behind or any sort of entry that they contribute. And sim options, this is kind of like the secret sauce for the various simulation hyperparameters that we also provide. And the sim results, which is essentially, again, as the name suggests, is the EM simulation solver results that we also provide to the Squads users. Again, optionally, people can give more information as well, but this get dataset info you can use to learn a little bit more about all the datasets available in our Hugging Face database. To get that dataset as a Python or as a Pandas dictionary, Pandas data frame, you can use the C dataset method, and as you'll see, it will return all the information available in this dataset as a data frame. Cool. And let's say now you're curious to see who contributed this dataset, or who contributed this simulation dataset. You can then use this view sim contributors off method to query for that. And as you'll see, my colleague Andre was the one who uploaded this dataset. And of course, we use this concept of digital twin to build this Squads database. So this dataset must have a physical device, a reference device, which was measured to create this validated dataset. And you can access that by using this view reference device off method. And this would kind of show you where you can find the design code for the measured device, any paper that it was published on it, the image of the device, the foundry where it was created, fabrication recipe. If people want to provide their entire fabrication recipe, we're actually partnering with FabuBlocks. On the next upcoming updates of Squads, people will have access to that as well. The entire fabrication recipe for device or for designs for, again, whoever wants to share that. So we have all these information on the simulated data sets. And again, if you just kind of are curious to see what type of measured devices are also available in Squads, you use this get measured devices method, and it will kind of show you data frame of the various devices that have been measured for the Squads project. And this did not render super well, but if you, let's say, have a measured device that you want to contribute to the Squads project, there's a very simple API workflow that we have that you can use. Again, I have on the doc site for Squads on tutorial 4. I talk about it in much more details of how to do so, but the idea is that you log into GitHub, so you just need to create a GitHub token, and you just use this contribute measured data with this new device entry dictionary, which again, this needs to be of a certain standard, which again is described in detail in tutorial 4, but that's it. You just run this method and we will get that information, and then we will, depending on the type of data, we will then accept your PR request and add it to the Squads database. So it's a pretty simple API workflow that we have to send your contributed, to send your measured data sets. If you want to also send simulated data sets that you've validated, you can follow tutorial 3 on the website to do that as well. And lastly, of course, Squads, Karim mentioned it's me as a solo developer, which sort of is true, but I am very thankful to all these people who have contributed to Squads in many ways. And again, I'm very excited to see what y'all also do for this project. And I want to see all's names on this list as well. Okay, now that we kind of know how to learn about datasets within the Squads project using the Squads API, let's learn a little bit about how we can use Squads to get the design space variables or the designs for our selected or desired Hamiltonian parameters. So this example that I have over here is for the case where, let's say, you just want a qubit. You want a qubit, and so the high level picture of how you do this in Squads is that you first define a system, then you specify the system, and then you do this method called create system df, which essentially merges all the data sets available in the Squads data frame to create one complete data frame, which contains information about both the Hamiltonian space parameters and the design space variables for the selected system. And it does so combinatorically. So this is a very crucial method whenever you have a system of more than one component. But for this example, we're dealing with one component, so let's kind of roll through with this. We just selected a qubit system. We then again specify what this qubit looks like. In this case, it's a transpond cross. For example, let's say you mistakenly put transpond ROS, it will tell you, okay, this is not supported. We only have support for these two type of qubits right now. So we do that, and then we run this important create system data frame method, which again, as you can kind of guess, will send back a data frame object now with the entire design space variable set, the EM simulation results, and this data frame is created, which we will then use to do further analysis on. So for that, we import this analyzer method, which is the second object in Squads that is very important. So let's import that. And we pass on to this analyzer method the Squads DB instance that we created earlier. We do that. And then let's say you did not know what is the Hamiltonian parameters available for the qubit system that you selected. So you can use this target params keys method to see what type of Hamiltonian parameters you can specify for the single qubit system. So it tells you that, okay, you can only provide for this case the qubit frequency in gigahertz and harmonicity in megahertz. So let's do that. Let's say we want a qubit with 4 gigahertz frequency and then a harmonicity of 200 megahertz. So we set that as our target params. It's a dictionary essentially. And then we will use this find closest method within analyzer to again find the closest simulated design with these target Hamiltonian parameters. One thing to note again, since we're trying to find something that uses a metric, we need to define what the metric is supposed to be. So natively, we have support for Euclidean metric, Manhattan, Chebyshev, weighted Euclidean, and of course, you can always pass in a custom metric, however you choose to define it. So in this case, let's just use our favorite Euclidean metric, and this numtop variable is asking the database for the 3 closest designs for this Hamiltonian parameter. So we run that, and that's it. We have found 3 qubit designs that will give us, and as you can see, these are kind of close. We wanted 4 gigahertz and 200 megahertz, very close to what we wanted. And it also gives us the EJ variable, from which we can back calculate the LJ variable, which is for people who are savvy with fabrication, that is a very crucial fabrication target that we would need to design our qubits. So we have all the information we kind of need right now to design our qubits. Cool. Let's kind of quickly show you all how to use a custom metric in Squad, because depending on your use case, you might want to use a custom metric. So in this case, I am defining a Manhattan metric. And how it works is you essentially call this custom metric func attribute of the analyzer object and set it equal to the definition of your metric, of your custom metric. And you then call or pass in the custom string to the metric in the find closest method to get the results using your custom metric. And let's see. Cool. It found the design that it found the closest design to your input or target Hamiltonian parameters based on your custom metric. As you can see, there is the design options column, which is the information needed to create Q components. So we extract that dictionary from this results data frame, and we save it as this variable best options. Now we're finally ready to create this qubit in Qiskit Metal. So we import the relevant Qiskit Metal files for this. Again, this is also, there was a question in the Discord I saw early in the morning, whether Squads requires Qiskit Metal or not in the environment. Absolutely. At the end of the day, you will be doing your design in Qiskit Metal, so it's absolutely relevant or required that you have Qiskit Metal installed, pre-installed, in fact. Okay, I imported all the Qiskit Metal relevant files, and now just creating a GUI instance for this design. And again, we are using this transmon cross Q component from Qiskit Metal, and we're passing it the best options parameter we just extracted from the Squads database. And as y'all will see, it creates that particular geometry from the Squads database. Cool. Now let's do a more important, at least experimentally important design use case, where you want to query for design space of a qubit and a cavity together. So for that, again, since we are all running the same kernel, I would advise always just unselect all to make sure that there's no data that you did not want the analyzer object to get. But again, it actually is handled in the backend, but just to be safe, you can always do this if you're running things in the same kernel. And again, in the same flow as before, you can select the system, which in this case is a qubit and a cavity class system. And then you kind of specify the system, which in this example, the qubit is a transmon cross, the cavity class just a CPW or rock meander CPW, and the resonator type, in this case, we want a quarter wave resonator. So this takes in value either quarter or half. So we specify these things. And again, just to make sure that the system that you selected is the one that you actually wanted, you can use this show selections method to get this printout, and everything looks correct. So let's move on. We're gonna create this. Since we are trying to define a system with multiple components, this create system df kind of merges them based on the shared key element that can be merged upon. So for the case of this qubit and the cavity claw, it's the actual coupling claw that on the back end merges the qubit data set with the cavity data set. So it's very important. We run that. And we can see what the data set looks like. There's 20,000 entries in this. And again, another pandas data frame with all the information that we need for further analysis. Similarly, as last time, you can also, again, if you're using the same analyzer variable, you can re-instantiate it with this DB object, or since we're in the same kernel, we can just use the reload DB method on the analyzer object, and it will automatically update the analyzer class based on your new selected system from your database. So just to again verify, you check that your selected system is a qubit and a claw. You can do the same method in analyzer, and yes, it did get updated. So that's another way to do this. Now for the qubit cavity system, there's 5 Hamiltonian parameters of interest. 1 is the qubit frequency itself. 1 is the cavity frequency. 1 is the cavity line width. 1, of course, the cavity type, whether it's a resonator, it's a quarter wave or a half wave resonator. The other one is the anharmonicity of the qubit. And the other thing is the coupling strength of the qubit and the cavity, the G value essentially. So for this demo example, we want a system with these values. So we redefine the target parameters dictionary. And again, in the same API format, we pass this target parameter to this analyzer object with our defined metric and how many entries we want. And it will find it for us. And this data frame essentially contains information on, again, as you can kind of see, the design options for the qubit itself, the simulation. This thing is kind of cutting out, but let's see if I can show it over here. Yeah, so we can get the design options dictionary for the qubit, the simulation parameters for that qubit, the people who contributed that qubit information, and same thing with the cavity claw, the design options for that, the simulation results for that, and all the Hamiltonian parameters, which I think is better seen over here, associated with this system. So everything is inside this results variable now. Okay, let's say now you want to see where this squad's, where this data point that, where this chip design that squads is giving you in this results variable, where it lies in relation to all the data that's available for this type of geometry within squads. To see that, you then you run this method called closest design in Hamiltonian space, and it will show you where your design lands in terms of the pre-simulated point. So as you can see, your target was this point over here, and here's a 4-dimensional thing, and the closest design found is actually very close to it. So that's how squad kind of functions in a nutshell. But let's say you're not happy with this. Let's say you want something that lands hopefully on the dot of your target parameters. For that, Squads has another feature called interpolation. I did post our paper on the Discord channel yesterday, but in the paper, just to give you all a quick summary, in the paper, we talk about how we can use the physics of the system, which in this case is this particular system of a qubit and a cavity, how you can, by understanding the physics, you can come up with some sort of scaling laws for the relevant design space variables to essentially scale them to match your target Hamiltonian parameters more accurately. So the details of this thing is in the paper. I would highly recommend I would highly recommend you all read this if you all are interested. But that scaling interpolator is found in Squads, which in this sub package. So we import that. And getting the design from the scaling operator is very simple. We just instantiate the scaling interpolator object with our analyzer class and the target parameters. And we then just use this get design method on top of this on the interpolator object. And we capture that in this design df variable. This printout again, this is more relevant. This would make more sense once the paper is read, but this is kind of showing us that, okay, this new design scales the kappa by this, the g by this, alpha by this, and resonator by this. And as long as these values are within like 10%, you should be fairly confident of your interpolated design. The design df object again looks similar to what we got from, or has information on the various geometries that would need to recreate this design in Qiskit Metal, which again, we access that similar to the last couple of times. And we pass this design options dictionary to this qubit cavity method. And that's it. So this particular geometry with values that correspond to, say, with values that correspond to all of this design space variables, this would give you the target parameters that you want. So that's what Squads does. Again, there's more helper methods, since again, this is a very minimal use case. You can, again, if you want to add wire bonds, you call this method. It will add wire bonds to your, sorry, not wire bonds, a transmission line with wire bond paths to your design. And next, you can then just export it to a GDS file by calling a toGDS method on this. So that's a very minimal use case of Squads. In the next tutorial tomorrow, I will actually show how you can use this API for, it is a very simple case, it's a demo case, but I will show how you can use Squads to create an actual ready-to-fab chip using Squads. So I think that'll be very exciting and very informative. And actually, we recently got devices from Lincoln Lab 2 weeks ago that were the first two devices designed with squads, and it's very exciting because the measured parameters are almost on the dot of where we expected them to be. So they're in the fridge cold right now, and after this talk, I'm actually going to run to the lab and measure them. But I hope this again kind of introduce what squads is to y'all, and tomorrow will be a much more active and more fruitful lesson of how to use squads and to create an actual fab-ready device. And I'll kind of also talk about the various design constraints and the various design rules that you need to think about when you're designing a quantum chip, as you know, in the flavor of what this Qiskit Fall Fest is all about. So that kind of concludes my tutorial for today. I realize I have a lot of time for questions. So I guess I'll address all of them.
Yeah, thanks for the great presentation tutorial. Okay, let me check the questions. And the first question is, how does the metric affect reaching the target state? Also, for someone who doesn't have access to real experimental data, what are the ways to contribute to the package in terms of design parameters?
So it's a two-part question, right? If I'm understanding it
Yeah, it
correctly.
is two questions.
So what is the first question again? Sorry.
The first question is, how does the metric affect reaching the target state?
The magic happen? Is that the question? So the magic is in the
Yeah.
paper. That's a cop-out answer. But the idea is that we love SC qubits. SC qubits is our friend. And in the back end of squads, we use SC qubits to essentially take the user parameters that squad gives us, talk to SC qubits, get some numbers back, and then present that number as a target. So again, it's all detailed in the paper. And of course, this data set or this squad's package is open source, so you can look into the code as well. So there's no magic. It's all real science, no magic. So I want to clarify that. Second question was people who don't have don't have actual devices, how they can contribute, right?
Yeah, exactly.
Cool. I mean, yeah, there's a lot of things that y'all can contribute to squads. I have a page on the doc site about the various type of contributions one can make, but just to reiterate those things, you can help with developing of squads. I have a wish list of the features that a community requested and some bug fixes and stuff like that. Please fork the repository, start addressing them. That's one way to go on about doing this. Second thing is, sorry. The second question, or the question was, they don't have a measured device, but they want to contribute the validated designs, right?
Repeat the question if you wish.
Sorry.
Yeah. For someone who doesn't have access to real experimental data, what are the ways to contribute to the package in terms of design parameters?
In terms of design parameters, okay. Yeah, sadly, since we only want to provide data to users that are validated, we have to have a reference device to match it onto. So we will not accept simulation results that are not mapped to a real life device. So we cannot really accept that, but there's various ways you can contribute to squads that is not just sending this design space variables. In particular, I think one of the projects that Walker will talk about, so I'm not going to spoil that, is kind of walks people through how they can contribute to squads that is not necessarily just programming stuff, but more so a little bit more science heavy. So I will not disclose that, but hopefully on whenever the project reveals will happen, you will know about this.
Okay, thanks. And next question is, if we have the custom component, can we use SQADDs to get the design options with desired Hamiltonians?
Yeah, I would. Custom Q component. So yes, so in that case, what I would do is, of course, since it's a custom Q component, it's not gonna work as nicely as you just passing on this design's options. But what you can do is then, let's say your custom Q component is, again, for the sake of example, is some weird CPW, let's say, right? And from squads, all you care about is the length of the CPW. So what you can then do is just extract this particular variable from the squad's output and put that in your custom Q component. And in fact, I'm going to show how to do this and how it would look like tomorrow in a more detailed example anyway. So hopefully that addresses the question if I haven't addressed it right now.
Okay. Another question is, can we use SQADs to get the design options of simulations?
Design options of simulation. Okay, if I am understanding the questions correctly, they mean the. Okay, let's look at this. Design DF, set up qubits. Sorry. Look. The simulation objects or the simulation parameters, I think that's what the question was, can be accessed. So that's it. So this is the simulation parameters used for this particular qubit simulation in ANSYS, and the second one for the cavity claw, you can see, you can get this as well. So everything is in the Quasar database, and I also have, and this is actually a question that was asked to Eli last week about like what the best ways are to learn about simulations and stuff in ANSYS. I believe there was a question like that, and there's actually a link in our doc site which kind of goes over the best simulation practices. So I would highly recommend y'all look at that as well. But yes, to answer this question, you can access all the simulation options from Squads as well.
Okay, thanks. And I think these are all questions for today. I think all of us need to grasp and get our hands dirty and Jupiter to
Yeah.
get involved, and we really encourage it to all to do this and follow up other tutorials from Sadman. Thanks a lot for this great, I think, tool and tutorial today.
Thank you for inviting me, and looking forward to learning more about y'all and talking more tomorrow.
Yes.